by the wall on the rod, then when the rod tries to fall, the static friction will prevent it from falling. We are looking at the minimum temperature. So at minimum temperature, the maximum friction should act, which is the maximum force of static friction, which can be taken as mu n. Mu n. So for equilibrium, what do we say? For equilibrium, mg must be equal to 2 mu n. And what is n? Well, n happens to be y alpha delta t into a. So solve for delta t, you get your answer. Delta t should be what? One more thing, what is mg? Mg is density into L into A into G. So A cancel. So you got the required answer as rho Lg by 2 mu y alpha, which is the answer for the 5th question. Yeah, is that okay? The 6th one. 6th one is straightforward. It's a question in the class I have done already. The only thing is numerical values are given in this question. Straight lift from a question in the class we did to a U-tube with different temperatures on both the sides, T1, T2. The solution, I think, if I remember the answer correctly, it was H1 minus H2 upon H2 T1 minus H1 T2 or some such thing. Yeah, what was that answer? Gamma equals, yeah, substitute, get your answer. 6th one. Yeah, is that fine? The 6th one?
Yes, sir.
We go to the 10th one. Before we do the 10th one, see I already got, what is the density of the solid versus to the density of the liquid? You must have found half the cube is floating such that half the volume is immersed. Is it not given there? The comprehension, just have a look at the comprehension section. Read the first line. A cubical block of solid floats in a liquid with half of its volume submerged in liquid as shown. Now if half of the volume is submerged, what is the ratio of the density of solid to density of liquid?
1 by 2.
Yeah, weight of the solid is equal to the buoyant force, which is, you will get like that. Weight equals buoyant force for the floating cube. So we notice that rho s by rho L equals half. We will take that into account while solving the question. So let's see. Which one did you ask for? The 10th one, yes. Imagine the depth of the block submerged the liquid does not change on increasing the temperature. Now, what is the, if you talk in terms of the depth, what is the weight will be, what is the weight of the cube? It's a cube, so we can take it as L0 cube into density of solid into G. This is the weight of the cube. And what is the depth immersed? Depth immersed is L0 square D. Let's call D is the depth into density of liquid into G. Can I say this?
Yes, sir.
This is the weight and this is the buoyant force. Now, imagine the depth of the block submerged the liquid does not change on increasing the temperature. Now, when you increase the temperature, what happens? First of all, Gg you can cancel. When you increase the temperature, L0 will become L0 1 plus alpha solid delta T, the whole cube.
So we can cancel L0 square.
Yeah, first we can cancel.
You can cancel it also. Okay, shall we do that? We'll do that. We'll simplify that. So you have L0 square gone and you are having D equal to L0 rho S by rho L. Now what is D dash? D dash is the new depth after it is heated by delta T. Now L0 will become L0 1 plus alpha S delta T. Okay. What about rho S? Rho S will become, and density of the liquid 1 plus You are getting it like that. Now, how do we, now if d dash is equal to d, that means what? These things
Equal to 1.
is equal to 1. So what you have is, shall I write it on the, I'll write on that side. The question I'm doing is the 10th one, right? So what you are saying is 1 plus alpha s delta t. Now alpha and gamma, these are pretty small. Okay, so how much will you get? Into 1 minus 3 alpha s delta t into 1 plus gamma L delta t. Basically these things,
Is equal to
if you multiply, only the first order terms will be there. Second order terms will cancel. They will be too small. If you multiply all of alpha into alpha is very small. Alpha into gamma is very small. So all this, just take the first order terms. So you have 1 plus, what do you have? Alpha s minus 3 alpha s plus gamma L delta t. That's it. Any of the second order terms when you are multiplying alpha into alpha or gamma into alpha, forget about alpha into gamma. That will be too small. They are all 10 to the power minus 5. Understand that. When you multiply 10 to the power minus 5, 10 to the power minus 5 become 10 to the power minus 10. Totally negligible. So if this is if this happens to be, when will this be equal?
1. Equal
When
to
this is 1. That means this has to be 0. If this is 0 only when gamma equals
12.
2 alpha. Gamma L equals 2 alpha s. That's your answer. That's the 10th one. We move on to the 11th question. Is it okay? The last one. 11th one. Assume the block does not expand on heating. The temperature at which the block just begins to sink in the liquid is. Now, the weight of the block, we will take it as volume into density of solid into G. But if it is going to sink, now density of the solid is not going to change because we are saying that you assume that solid does not expand. If it expands, the density will become rho s upon 1 plus 3 alpha s delta t. We are not going to take that because it is given there. Now what is this is equal to, when it just sinks means what is the volume displaced? The volume displaced will also be V. And density of the liquid will be what? Density of the liquid will be density of the liquid upon 1 plus gamma liquid delta T, because this was the density earlier.
Into G.
So when you increase it like this, and this is equal to G. So if you look at it, V and G cancel, Vg cancel. So what do you get? You get rho s by rho L is equal to 1 plus gamma L delta T. But rho s by rho L is equal to half. If you compare these two, this must be equal to 1. Delta T into gamma L is equal to 1, or gamma L, delta T equals 1 by gamma L. So what is the new temperature? The new temperature is original temperature plus delta T, which is T plus 1 by gamma. That's the required answer. Yeah, look at the question. So 11th A choice is what I have justified now. So let me introduce the next topic. We'll do a small section there and then we will continue with that next time. So we're starting off with calorimetry now. So you have done all the questions on HC Verma, you have completed thermal expansion. So let's see the next topic, the calorimetry. Calorimetry is the kind of is accounting in heat. So consider this: we have a vessel which is having ice at minus 20 degrees centigrade, let us say, and you are heating this vessel. So when you heat this vessel, let's say you also have a thermometer inserted inside it, which can give you the temperature. And let us see what happens if you make a graph of temperature versus, either you call it the quantity of heat or time. Why I'm saying it is because the more the time you put it on the burner, more is the heat transferred to the vessel. So what you notice is, initially the thermometer races ahead. So as time passes, temperature consistently increases. But then there comes a plateau. it is as if the burner has got off or thermometer is not working, but neither is true. Have a patience. You'll notice that the thermometer comes to life once more. It rises again. And we also notice that at this point you have ice, and when it was stationary, the ice is becoming water.
Yeah.
Rather, when the whole of it becomes water, the water temperature rises again till at a time it comes to a plateau once again, where the water tries to become the steam. When the whole of it has become steam, the graph rises once again. So both, when the ice becomes water, that is the melting point, or the water becomes steam, the boiling point, the temperature is temporarily stationary. Now, the boiling point is 0 degree centigrade, and melting point is 0 degree centigrade, and boiling point is 100 degree centigrade. If the pressure is 1 atmosphere, we are dealing with the pressure as 1 atmosphere. That's why you kept the vessel open, so 1 atmosphere pressure will act there. Can you tell me why do we use a pressure cooker to cook maybe rice? What is the advantage of using a pressure cooker?
It increases the boiling point.
Yeah, it increases the boiling point. Now that's the point. We are dealing with this at 1 atmosphere. If the pressure is more, then this might be more. So you can do their cooking at a higher temperature. That's the idea. But that was just to bring this point in that 0 and 100 are only true for 1 atmosphere. But in our course, we are dealing with this only. Okay? Now, what we say is the heat transfer, we depict it as Q equals ms delta T. In a given phase, Q equals ms delta T. Q is quantity of heat, m is the mass, s is the specific heat, delta T is the change in temperature. Rather, what is specific heat? We do it the other way around. Specific heat is Q by m delta T. For example, specific heat is amount of heat required to raise the temperature of unit mass of a substance by 1 degree centigrade. For example, water, we say it is 1 calorie per gram per degree centigrade, like that. You can remember it for ice also, it is 0.5 calorie per gram per degree centigrade. Chemically they may be same, but physically they're different, they have different specific heat. Steam will have some other specific heat. It will be given to you in the question. So, we know this. Water, we say, has a high specific heat. Water is used as a coolant. It requires quite some heat to raise its temperature. In terms of a cooking medium or what we eat, can you tell me some substance which has low specific heat? In terms of what we, it's a substance that we eat. So, yes, oil. Oil boiling point is very high. It boils very quickly. The moment you put it on the gas, it will start boiling. Because a small heat will make it boil. Its temperature rises very fast. Whereas water, it will take quite a long time to heat it. Okay? When you are cooking, in a hot food, what are you interested in? What is important? Is the heat important or temperature? When you are cooking, what are you interested in? The heat or the temperature?
Heat.
Does hot food give you more calories than cold food? Yeah, what? Does a hot chapati give a more calorific value than a cold chapati? What do you mean yes? You don't get any heat, more calorific value out of a hot chapati. Why do you eat a hot chapati? Only for taste. Do animals eat hot food? Does a buffalo eat hot chapati? It eats any kind of a junk. Any doubt about the strength of a buffalo? You only heat something to have taste. It is only for taste. If you don't mind, you can have cold food or hot food. Yes, some people might say it helps digestion, etc. But these are very insignificant stuff. Buffalo doesn't bother about it. It has all the digestion, all the strength. So your heating is only important in terms of temperature. That's why all the fast food centers will use oil rather than water, because oil is faster to cook. Of course, it has a different taste, or you could say a better taste. That's the idea. So oil has less specific heat. Now two things. You can understand specific heat in terms of, if you talk in terms of a human behavior, it is like saying that the event and the temperature. Some people get angry very fast. So चाय गरम क्यों है? या चाय गरम नहीं है, ठंडी है, चाय ठंडी क्यों है? So you say चाय ठंडी है तो क्या हो गया? इतना गुस्सा क्यों आ रहा है? आप इतने गरम क्यों हो रहे हैं? So the event is small. The temperature is high. The anger is very fast. So this person is like an oil personality. And somebody else could be very cool. भाई साहब आपका घर जल गया. ऐसा क्या? अरे आपका घर जल गया, अब जल ही गया कर क्या सकते हैं? So now this person is not responding at all. It need not be so cool either. So that's like a water personality. So there are oil personalities, water personality, like that I'm saying. So somebody who can get very angry very fast is low specific heat, and some cool person is high specific heat. The same thing happens in terms of land and water. In geography, that plays a huge role. Well, even see in Bombay right now, all the students in my class are wearing t-shirts. I'm noticing right now all of you are wearing sweaters. How come? Are we not in the same country? Some of you are wearing a coat and all that. So we can't imagine wearing a coat here. You can right now see I'm just wearing a shirt, and not that I've taken off my coat or something. So how come we have these differences? Because Bombay is a seaside climate. The land, when the day comes, the land temperature goes up very fast and sea is cold. And hot air rises above the land and cold air from the sea comes towards the land. You got a sea breeze during the morning. And at night the reverse happens. The land cools down very fast. The sea, after getting heated up all the day, the hot air is above the sea. Now the cold air from land will go towards the sea. So you have the land breeze. So a seaside climate is always moderate. You don't have any extremes. And land side you can understand Delhi climate, or for that matter Sahara is too extreme. A Sahara desert type of climate. In the mornings you will have temperatures like 50 degrees centigrade in the noon, and at night you have minus 20. Now how do you live there? 70 degrees centigrade variation in a single day. So that's because of the specific heat of land is low. General idea. Tell me, should a thermometer have low specific heat or a high specific heat? Why low? Yeah, we would like it to be sensitive. It should take a little amount of heat and immediately report the rise in temperature. Well, that's the idea. So let's do the first question pertaining to this. Note down, 0.2 kg of metal at 150 degrees centigrade is added to a calorimeter. Is added to a calorimeter of water equivalent 0.025 kg containing 150 cc of water at 27 degrees centigrade. The final temperature of the mixture becomes 40 degrees centigrade. 40 degrees centigrade. What is the specific heat of the metal? It is added to a calorimeter of water equivalent 0.025 kg containing 150 cc of water at 27 degrees centigrade. The final temperature of the mixture is 40 degrees centigrade. What is the specific heat of the metal? Now before you do the question, there are two phrases I have used which I haven't talked about before. Let me clarify them. One, calorimeter is a vessel in which we perform these experiments to ensure that there is no leakage of heat. It's usually a copper vessel surrounded with thermal wool, etc., kept in a closed box containing mirrors, and the box is closed. So we try to